So now we will be going ahead and reviewing the general linear programming problem in theory. In the following video, we will be solving the same type of problems using Microsoft Excel basically. Alright, so here is our linear programming problem, an example basically. So in this example, we have an objective function. So this is our objective function. And these are the two constraints, right? So these are our constraints. The thing that makes this a linear programming problem is that both the objective function and the constraints are linear. Linear here, linear here. Linear, it means that the exponents of the x and the y are all 1. Do you guys see that? They are indivisible ones here, to the raised to the first power. So because all the objective functions as well as the constraints, in this example we have two constraints, both inequality constraints are linear in form, so this is a standard linear programming problem. So the key idea in linear programming problems is that the solutions, the optimal solutions, in this case it's a maximization problem, the optimal solutions are corner solutions. All right, so if anything, so we need to write it as a remark. Solution of linear programming problems are at corners. So what does that mean? So what we will do is the following. We will first start, and this is a standard method by the way, we will first start by looking at the constraints. So first, draw the map of the constraints. And by the way, there's two invisible constraints here as well. So in total, we have 4 constraints. Let me do it in green color. So there you go. So we will go ahead and we will be in the first quadrant, x, y. Why? Because look at that, x and y are both greater than or equal to 0. Then what I will do is to draw these two additional constraints. So we are in the first quadrant for sure because both x and y, x is greater than or equal to 0 and y is greater than or equal to 0, which is the first quadrant. And 2x plus 3y is equal to 180. If you draw that line less than or equal to 180, it will hit the x-axis at 90 and the y-axis at 60. So maybe 60 here, and maybe I'll go ahead and it's so there you go, 90 there, and I will go ahead and draw the line. There you go. So that is the first constraint, and because we want to be less than or equal to the sign, so we want to be below this line, right? So this line is 2x plus 3y equals 180, and because we want less than or equal to 180 according to the problem description, we are over here in the first quadrant below this line. There you go. Now we can go ahead to the second part, and for the second constraint, oops, let's use the same color, green I guess, or let's make it back to blue or gray. Gray is a good color. Okay, so for the second constraint here we have 3x plus y is less than or equal to 135. So let's first go ahead and draw the line 3x plus y equals 135. Set x equals 0, y comes out as 135, somewhere here, 135. And set y equals 0, x comes out as 45, so somewhere in the midpoint, 45. And now we can go ahead and draw the line. There you go. And like in the previous case, we want to be below the line. All right, so let's just go ahead and draw the line in blue. Let's hope that it will give us green color. Yay! The intersection, if you mix yellow and blue, that should give you green, right? One of the first skills we learned in elementary school. Awesome. So what happens is the following. Because the conjunction is and, you want to satisfy both of these constraints at the same time. Oops, let me just go ahead and make sure I write the equation of this one is 3x plus y is equal to 135, and we want to be below that. That's why I highlighted the line, the area below that line. All right, so because the conjunction here is and, we want to have both conditions satisfied, and both conditions are satisfied in this region. So this is the area where both conditions are satisfied. Next, now it's time to draw in the objective function. Let's just go ahead and use green color. So this is our objective function, x plus 2y, but draw how, right? So because we don't know which value it's equal to, what we can do is we can draw some various. So for instance, x plus y equal, sorry, x plus 2y, I should say. X plus 2y, we can try different values. For instance, if I want to draw x plus 2y equals, say, 60, how will that look like? Well, first of all, setting y equals 0, x is 60, and setting x is equal to 0, y is 30. So it is a line like, and it has a slope of minus 1/2, which is unfortunately very close to the slope of minus 2/3, I'm assuming, right? So it will look like this. Do you guys see that? Let's try something else. For instance, how about the one, so this one is a 60 here, and this one is a 30. There you go. How about, how about the line which goes through that point y equals 60? Well, for that one, I think you guys would agree that because I want y equals 60, when I set x equals 0, that will happen if the whole equation is equal to 120. So it goes through that point 60, but at the same time, if I plug in y equals 0, x is 120. Oh, I see what's going on. So this is where 120 is. The line is something like that. There you go. Do you guys see that? And so on. So for instance, I can next try, for instance, I don't know, x plus 2y equals, for instance, 270. Setting x equals 0 will give you y equals 135, and y equals 0 will give us x equals 270 way over there, somewhere far away. All right, so you guys can see 3 different level curves. Now, our goal is to shift this line as northeast as possible, because those values keep increasing as we go northeast. This is the one associated with the value 60, this is the one associated with the value 120, and this one is associated with the value of 270. Do you guys see that? X plus 2y is equal to those 3 values, 60, 120, 270. So we want to see what is the highest that I can drag that line such that it still keeps touching that area, and you guys can see that that point is right that, and that's the solution basically. So therefore answer is that x plus 2y is maximized when maximum when x equals 0 and y is equal to 60. And indeed, the value of our function will end up being the second one, right? X plus 2y is equal to 0 plus 2 times 60, and that's 120. Now, you can try different points inside that green area region, and you will see all of them will have a value which is lower than that, lower than 120. Just as an example, if we were to substitute 45, 0, right? So how example, if we were to plug in x, y as 45, if we try this point, let's see what comes out. X plus 2y is equal to 45 plus, 45, 0, I should say, not 60, 45, 0, sorry for that. 2 times 0, hey, that's just 45, which is clearly less than 120. Do you guys see that? So yeah, so that clearly shows us that the optimal point is right here. So suddenly you realize, I hope, that the whole idea depends on the slope of this line, right? Which is of this function or line, if you want to call it. So this is the same thing as this one, x plus 2y. So do you guys see that? The slope here is minus 1/2. In fact, the slope of all these 3 lines, the slope here, slope equals minus 1/2. The slope here is rise over run is minus 1/2, and this for this one, and similarly the slope of that one is equal to also minus 1/2. So now the whole idea is to compare the slope of the objective function x plus 2y with the slopes of the 2 given constraints, and when you check those slopes of these two, the slope of this one will end up being minus 2 over 3, and the slope of the second one is minus 3. Do you guys see that? And ultimately it is the slopes which determine which of the corner solutions will end up being the solutions. When I say the corner solutions, what I mean is the corners of the region defined by the constraints. Remember that we said the green region is the key region. In this particular case, the solution ended up being that corner over here, right? For our problem, that's the answer. But because there are in total 4 corners of that shape, right? 1, 2, 3, 4. We knew from the beginning that one of these 4 corners is the answer. So an alternative way to solve this problem without drawing the lines is just to evaluate the function, the objective function, at those 4 points. So let me just go ahead, and I think I already evaluated it at one of the points, and we clearly saw that 45 is less than or equal to 120. Let me just go ahead and evaluate it here as well. Clearly at this point, our function x plus 2y, 0 plus 2 times 0, that will be 0. It will have a value of 0. The only remaining point for which I did not calculate the value of the function is this point over here. So how do we calculate the coordinates of this point? Easy. All we do is just solve the 2 constraints simultaneously. Let's just go ahead and do that. 2x plus 3y is equal to 180, as if they were equalities, and 3x plus y is equal to 135, depending on your on the way you learned this concept in middle school. One idea is just to use a substitution trick. So y is equal to 135 minus 3x, and substitute this value of y into the first equation. So as a result, the first equation becomes 2x plus 3 times. Replace the y with 135 minus 3x, and that is equal to 180. So as a result, so we have 2x minus 9x, so that's minus 7x, plus 3 times 135, which is 405, I think, is equal to 180. And finally, that will give us x is equal to 405 minus 180. It's 400 minus 175, which is 225. 225 over 7. There you go. So that is the x component, and for the y component, all you do is plug that value into this. 135 minus 3 times 225 over 7. So that will end up being, okay, let me just quickly use a calculator here. Just do the common denominator. 7 times 135 is 945 minus 945 minus 3 times 675. Yes, that would be correct. 675 minus 675. Okay, so it will end up being 270 over 7, I should say. 270 over 7. And one thing you can do is you can just plug in these 2 values into the original 2 constraints, these 2 equations. Let me just go ahead and highlight them. This one and then this one, to see if they really satisfy the desired equation, which I think they do. So which is pretty good. Let me double check that. 225 times 2 is 450. 450 plus 810. 450 plus 810. Let me double check. 450 plus 810 equals 1260. And when I divide it further by 7, that better gives me 180, which it does. Okay, good. So these are the x and y coordinates of that remaining point. So the only thing left is just to plug in these 2 values into the objective function and see that whether it is less than or equal to 120 as in the previous case. Let's quickly check that. So for that point, we have 225 over 7, 225 over 7 plus 2 times 270 over 7, and and that thing comes out as, let me quickly check, 540 plus 225 equals 765, all divided by 7. 109.29, 109.29, which is 109.29, which is clearly less than 120 as well. So therefore, the value of our objective function, that green function, happened to be at that vertex, it happened to be 120. At this vertex, it happened to be 0. At this vertex, it happened to be 45. And finally, at this vertex of this green quadrilateral, it happened to be 109.29. All the remaining 3 values are less than 120, that corner. So therefore, the maximum value of our objective function is 120, and it happens in that corner. So as a result, solution, the maximum value of x plus 2y equals 120 exactly when x equals 0 and y equals 60. That's it. At x equals 0 and y equals 60, the value of our function is 120, and that's the maximum value. Now what I will do next is just let me go ahead and modify the problem slightly. So in a sense that instead of the objective function being x plus 2y, so what if it was let me think about it. So instead of -1/2, I want it to be a little bit steeper. How about x plus y instead? So what if the objective, so all the other constraints were the same, except that now the objective function is x plus 2, x plus y. Inquiry. So we inquiry. Oops. This what if objective function were what? X plus y instead of x plus 2y, ? Well, so the new problem that we want to solve is this: maximize x plus y, where x and y are greater than or equal to 0, subject to the two constraints are still the same constraints, namely 2x plus 3y is less than or equal to 180, and the first one was the second one, 3x plus y is less than or equal to 135. So we would have done pretty much the same thing. Let me just go ahead and move this a little bit down, so this way it can fit the page. There we go. Okay. There we go. So what if the objective function was this? All right. There you go. Okay, so in that case, see what happens. Well, first of all, because the two constraints have not changed, x-axis, y-axis, we still have the same region. Namely, if we start with the first condition here, 2x plus 3y equals 180, less than or equal to 180. Well, first of all, if you plug in y equals 0, 2x equals 180, x equals 90. And let's put it here, x equals 90. And if you were to plug in x equals 0, y would have come out as 60. Maybe somewhere here. And as a result, that would have been the first constraint. And we want to be below this line. So let's just go ahead and, just like in the first question, let's just draw it in yellow color here. And similarly, the second condition, namely this one, if you plug in y equals 0, 3x equals 135, x is equal to 45, midway. There you go. And then if x were 0, y would have been 135, somewhere here. And let's just go ahead and draw the line, and as well as the blue underneath, and let's see if we get a green color again. Oh, so that's so satisfying, right? That's pretty good, actually. There you go. All right, so therefore we want to be somewhere on this region, and because this is a ultimately we have a linear programming problem where the constraints is linear, we know that the answer should be one of these four corners. 1, 2, 3. For one of these four, when you plug in these values of x and y in those 4 points, will give you the maximum value for x plus y. So the 4 candidates are 0, 0. And we need to evaluate the function at that point. The other candidate is 45, 0, namely this corner over here. The other candidate is 0, 60. And finally, the last candidate, which we already calculated, it was 225 over 7 and 270 over 7. So it was 225 over 7 and 270 over 7, the coordinates of that point. All right, so 225 over 7 and 270 over 7. So what we can do is we can directly plug in the values into this function. So first, when we plug in 0 and 0, that thing comes out as 0. I doubt this will be the maximum value, right? So next let's plug in 45 and 0. 45 plus 0, that's 45. So that, at least that's better than that one. So that can definitely not be the answer. Next is 0 and 60. So 0 plus, hey, this one is yet better than the previous two. So this can't be the answer either. So far, our running maximum is this one. Let's check the very last one. 225 over 7 plus 270 over 7. When you plug into this value, x and y are known, so we get 495 over 7. Do they simplify? Let me check my calculator here. 495 all divided by 7 equals 70.71. Okay, so this is approximately 71, or let's just not round it, 70.71. Hey, this is the maximum value. So it turns out that I claim this must be the answer. So this is the one which have the maximum value. Comparing to this one, suddenly the solution changed, but it's still a corner solution. Do you guys see that? So therefore, this is the actual answer, not this one. The correct answer is, oops, let's put a check mark. This one. This one is where the function x plus y is maximized. If you wonder why such a thing happened, it's this time because of the slope of our objective function. Previously, the slope was -1/2. The slope of this function x plus y, if you evaluate it at different points, you realize that the slope is -1. For instance, if I were to draw this, let's draw a couple of hypothetical ones. Let's first draw x plus y equals 45, that line. I'm interested in the line x plus y equals 60, then at the line x plus y equals 90, and I'll also go ahead and I'll draw x plus y equals 135. See what happens when I draw these hypothetical lines. So we have the 45, it will go like this. The 60 will go like this, the 90 will go like this. All of them has a slope of -1, and finally the 135 should go like this. So all of these 4 lines, obviously the values of those lines keep increasing as I go northeast. But do you guys see, if you start from that one, the one at the bottom, let's just write it out here. So this one is x plus y equals 45. By just keep sliding it northeast by preserving the slope, I reach to that next stop, right? X plus y equals 60, this one. But I can keep doing better. I can still obtain some points in that region. So the furthest I can shift it is this one. Oh, this is the one. And this one turns out to be, if you write out the equation, x plus y equals, well, we just did it. 495/7. So this is the max. Well, this line, this one, is x plus y equals 90, is higher than x plus y equals 495/7. However, it's not attainable because it's not touching any of the points in the green region. Do you guys see that? So therefore, solution to updated or revised linear programming problem is now what? When I say solution, the maximum, right? So when I say solution, I mean the maximum is now a maximum of 495/7 for f of xy equals x plus y, and this is achieved when what? When x is equal to 225/7 and y is equal to 270/7. Does that make sense? So the solution in this case is still a corner solution, but now it's another corner. In the previous case, it was again a corner solution, but it was this corner. Now the solution has moved to that corner because we changed the objective. The slope of the objective line determines when I shift the objective line as northeast as possible, what will be the last point still touching that line, right? So that's the key idea. Hope you guys enjoyed it, and looking forward to see you guys in an upcoming video.